Today we continue our study of industrial hydraulic technology with the hydraulic transmission of force and energy. In hydraulic systems, energy in the form of pressurized liquid flow is transmitted and controlled through a conduit system to an actuator at the point of work. Liquids have a few characteristics which make them an excellent means for transmitting energy. They take the shape of any container you put them in. They are relatively incompressible, and when a force is applied to a confined liquid, it is transmitted as pressure equally in all directions. This particular characteristic of liquids is called Pascal's law, named for the man who first discovered the relationship of force, pressure, and area. Pascal's equation looks like this. Pressure, usually measured in pounds per square inch, is equal to force in pounds divided by the area in square inches. Monitoring the pressure of the fluid is one way to determine how well the system is operating. Two types of pressure gauges most often used to monitor industrial hydraulics are the Borden tube gauge and the plunger gauge. A Borden tube gauge basically works on the same principle as this party noisemaker. It has a curved metal tube which has a gear linked to its end. Just like the noisemaker, when pressure is applied to the opening, the tube tends to straighten out. The more the pressure, the more it straightens. This movement then is transmitted to a second gear, which has a needle pointer attached to it. The needle, in turn, points to the pressure reading calibrated on the face of the gauge. Borden gauges are precision instruments, capable of readings as accurate as 1/10 of 1%. But they are relatively delicate, and the pulsations in most hydraulic systems could quickly damage them, unless some provision is made to isolate them when not in actual use. Sometimes a device called a snubber is used. It's installed in the line between the gauge and the system. It works by stopping or restricting fluid flow to the gauge, so any pressure surges or pulsations are smoothed out before they reach the gauge. The plunger gauge consists of a movable plunger connected to system pressure, a bias spring, a pointer, and a scale calibrated in pounds per square inch. As the pressure in the system rises, the plunger compresses the bias spring. As the plunger moves, so does the pointer connected to it, indicating the appropriate pressure on the calibrated face. While not as accurate as Borden tube gauges, plunger gauges are a more durable and economical means of monitoring system pressure. Now, to convert hydraulic pressure into mechanical force, we can use various types of actuators. The most common type of actuator used in hydraulic systems is the cylinder. Hydraulic cylinders take hydraulic pressure and change it into a straight line mechanical force. This straight line force is frequently called linear mechanical force. Hydraulic cylinders basically consist of a cylinder body, a piston rod attached to a movable piston, and a closure at each end. This is called the rod end because the piston rod goes through it, and this is called the cap end. Most cylinders have holes called ports at each end. The inlet port allows the hydraulic fluid to enter the piston chamber, and the vent port allows the fluid to exit. When a force is applied at point A here, the resulting pressure is transmitted to the piston in the cylinder. The pressure pushes on the piston, resulting in a mechanical force here at point B. Remember that one of the major advantages of hydraulic systems is that they can be used to generate large mechanical forces. Let's say we want to use 5,000 pounds to move a 7,500-pound load. Here at the input end, we apply a 5,000-pound force on a piston with a 10 square inch area. Okay, by applying Pascal's law, which says pressure equals force divided by area, we come up with 5,000 pounds of force divided by 10 square inches of area, which gives us 500 pounds per square inch of pressure in the system. So here on the other side of the piston, we have 500 pounds per square inch of pressure pushing against this larger piston, which has an area of 15 square inches. Now, since we already know the pressure, we want to find the force here. Our equation becomes force equals pressure times area. So our output force is equal to 500 times 15, or 7,500 pounds. We are able to increase the mechanical energy of a 5,000-pound weight enough to move a 7,500-pound load. Sometimes we need to increase the hydraulic pressure in a system. We can do this by using a device called an intensifier. Basically, an intensifier is a big hydraulic cylinder and a small hydraulic cylinder whose pistons are connected together with a piston rod. To show how it works, let's apply an initial hydraulic pressure of 500 pounds per square inch against this large piston, which has an area of 20 square inches. This gives us 20 times 500, or 10,000 pounds of force, which is transmitted through the rod to the smaller piston at the other end. The 10,000-pound force is now being applied across only 5 square inches of surface, creating a pressure here of 2,000 pounds per square inch. So our initial 500 psi pressure has been intensified to 2,000 psi at this end. Up to this point in our examples, we've used a force on a movable piston to generate our pressure. This device is called an accumulator. An accumulator stores hydraulic pressure as potential energy. This stored pressure can be turned into working energy, that is, flow and pressure. One of the drawbacks when using an accumulator is that it has a specific capacity. Once its fluid is used up, the work stops. To get around this, we need a way to provide a continuous flow. The device we use to do this is called a positive displacement pump. It has a plunger encased in a housing. The plunger is connected to a source of power, usually an electric motor, which moves it back and forth. There are valves connected at both the inlet and outlet ports, which allow flow in only one direction at a time as the plunger moves. When it moves in this direction, the volume inside the chamber increases. The inlet valve opens and fluid from a reservoir is pulled in, filling the chamber. When the plunger reverses direction, the inlet valve closes, and then as the volume in the chamber begins to decrease, the outlet valve opens, allowing the plunger to force the fluid out into the system. As the plunger cycles in and out, an intermittent or pulsating flow is produced. Although reciprocating plunger pumps have a place in industry, usually in very high pressure applications, a more commonly used positive displacement type pump is the rotary pump. It's basically a housing with inlet and outlet ports and a rotating group which develops a smoother fluid flow and pressure. One style is the vane pump. In its simplest form, it looks like this. The rotating group consists of a rotor and movable vanes. The rotor is offset to one side of the housing, and the vanes are free to move in and out. When the rotor is turned, the vanes are thrown outward by centrifugal force, forming a positive seal here. The increasing volume here on the inlet side allows liquid to fill this area, while the decreasing volume on the outlet side here forces the liquid out into the system. In a hydraulic system, there is a direct relationship between pressure and resistance. How much pressure a pump develops depends on how much resistance it encounters. This resistance basically comes from two sources: the object's resistance to being moved and the fluid itself. If there were no fluid resistance, the pump would only have to generate enough pressure to overcome the object's inertia and friction. However, since fluid resistance is always present in a hydraulic system, the pump has to produce more pressure to overcome it. Notice that the gauges indicate highest pressure here, close to the pump, and decreasing pressure here, here, and here, the farther we go along the system away from the pump. Since energy cannot be destroyed but can change form, this loss of pressure shows up as heat. It is caused by the friction of the molecules of the fluid rubbing against each other and the walls of the system piping. Hydraulic systems can be designed to reduce heat generation by minimizing the number of bends in the line and by using the proper size tubing. Altering the size of the tubing can affect both the flow rate and the velocity of the fluid in the system. Flow rate is the amount or volume of fluid which moves through the system. It is usually measured in gallons per minute or GPM. Velocity is the speed of the fluid as it moves through the system, usually measured in feet per second. Increasing either the flow rate or the velocity will increase the friction, and therefore the heat which the system generates. The relationship between flow rate and velocity can be shown with these two pipes. If we want the fluid to move through both pipes at a flow rate of 5 gallons per minute, the fluid moving through the smaller pipe will have to move faster than the fluid in the larger pipe. The additional friction caused by the faster moving fluid will create more heat. Another factor that influences the efficiency of a hydraulic system is the hydraulic fluid that's used. In our next lesson, entitled Hydraulic Fluids, we'll take a close look at the various characteristics of hydraulic fluids and the effect they can have on hydraulic systems.